Okay. Lecture 8, Parallelism of a Vector. We still are in the differential geometry, attention now, extrinsic geometry, 3D. Okay? Now, this subject is quite important when, for instance, you're going to study in the videos, okay, ahead, you're going to study the application of this to the Riemann curvature, okay, and rich tensor curvature and rich scalar curvature. So curvature are related, okay, to the Christoffel symbols, okay, and this concept of transport we will use to express the Stoffel symbol of second kind in terms of the metric. Okay? The objective is express the whole geometry, okay, extrinsic geometry in terms of G, the metric. Okay? That's the objective, because metric will be used in the intrinsic geometry, okay, and Einstein's equation, that's a fundamental. Rather, are only metrics. There is no vector, position vector, no cross product, no dot product, okay. That's why metric is crucial. Now, let's go ahead and explain parallelism of a vector. Consider this curve. Gamma is a function of the parameter t. Sometimes the literature you see lambda instead of t. So this here is related to the xi. Okay, xi depends on this gamma of t. Okay, so point P, point Q depends on t to get the xi. Now let's do this. I would like to emphasize that this is a vector space, not dual, and then I have xi, eta j, xi, yj, and so on. Okay, this is attention. These are components of a contravariant component of vectors. Okay, these are coordinates. That's attention now. See, a vector, for instance, a vector xi, xj, you see, is a contravariant components. Okay, they belong to the space vector. This is space vector, not dual. Okay, we are just working with the space vector v. Now, I consider this curve. This is point P, this is point Q. That's a curve. Okay, xi depends on t. Now I have the vector y, and the vector y here is parallel. Okay, transported. Y here and y here. Attention now, parallel transport, parallelism, is only on the same curve. The same curve xi. If you move to another curve, there is no way to talk about parallelism, which I mention here. On the same curve, we will talk this later. Okay? Now, assuming parallel transport, okay, y at p vector is identical to y at q, p and q, along the curve gamma t, meaning that, you see, parallel transport is this over here. What this means? Means that its covariant derivative along the curve, same curve, must vanish. how I represent this here, this covariant derivative of y with respect to the vector x is equal to 0. X vector s is a first order tensor. You see, if I want parallel transport to a second order tensor, I just substitute y by a second order tensor, and so on, third order tensor, and so on. Okay, so this is a definition. Okay, the parallel transport of vector y along the curve, right, which I have the vector x. This is a tangent vector. See, a tangent vector. Okay, now this is a coordinate eta j. Okay, related to the vector y. Now, this is item 1. Item 2, expressing the parallel transport condition. Okay, I'm just going to open this, and in this case, okay, expand. So, the covariant derivative of vector field, now I'm working with the components. Attention now, contravariant component, which belongs to the vector space along a curve in this direction, xi, you see, upper and upper, is given by xi. I just copy this equation here to there, just using the component, okay, the contravariant components. I here, okay, is covariant because this corresponds to a partial derivative of ci. Okay, I upper is in the denominator, okay, as I said before. This is equal to 0. Now I substitute, since x bar is dxi over dt. See, that's a, look how interesting, You see, this xi, sorry, this I here is upper, okay? I just, you see, free index I here upper, I upper over there. So it's consistent. Now I substitute here to here, okay? That's it's clear, no problem. You see this xi here, I substitute here, okay? Substitute here, and also this over here, okay? And that's expand. Now, this I can kind of cancel. So this leads to the derivative of y with respect to t, okay? Because the vector also varies with t, okay? Remember that t is a parameter, okay? So this curve here is called a parametric curve, okay? Depends on this scalar lambda. So this is equal to 0. Then I repeat here the same equation over there, okay? Is equal to 0. Now, the third item. Define the deviation vector, attention now, eta k. Eta k, attention now, is coordinate belong to the vector space because I have eta k over here and eta k over here, eta j, so it doesn't matter. Now, the vector y remains the same on the parallel transport, attention now, as I said before, on the same curve, gamma t, meaning that its components remain constant when expressed in a coordinate base adapted to the parallel transport. Okay? Now that's important this. Here I'm talking to the vector. Okay? The vector remains the same. Obviously, the coordinates, okay, the components will change. No? The components of this vector y here and here, the component of y, in this case here, will change from here, okay? The basis vector will change from here to here, but the vector y is identical to this y. That's why this is the proper tool, okay, to represent these two variations, okay? variation from point and variation from the component. Okay? Now, then I can write from here, I just substitute, okay, yj by eta j. So this is the equation here. If you set yj is equal eta j, okay, which is the coordinate, okay, in this direction over here, okay. Now that's equation. This equation describes, attention now, how components of y, you see, eta j, they are components of y, how it involves along the curve when parallel transport. You see, when I parallel transport, okay, attention now, the components will change. The components from here to here will change. So this is the equation which shows, okay, how it changes when I move t here. And I move t, I'm moving ci. You see, that's quite clear. Okay? This is a very important, as I said, very important result. Okay?